Hi, I'm Kevin Weller, a certified FME and FME server professional, systems integrator, GIS bootcamp instructor, and software engineer by trade. I tend to push the envelope when it comes to treating FME workflows as custom software, requiring modular architecture, automated testing, and other software engineering methods. I own Modern Geosystems, a safe software service partner specializing in comprehensive geospatial solutions architecture, implementation, and application development. We're often serving clients with complex requirements involving advanced FME server and cloud deployments. One such client needed an up-to-date replica of their Salesforce data, including location data, in an Esri-compatible PostGIS Enterprise geodatabase, so they could more easily integrate it with other enterprise data, including geospatial studies involving a high-availability ArcGIS Enterprise deployment we installed for them. Between Salesforce and their geodatabase, they needed changes in one to be reflected in the other in near real time, so everyone would be on the same page, including sales staff, managers, and geospatial market analysts. So I decided to implement a bidirectional data synchronization scheme using the relatively new Streams feature in FME Server. Streams are a powerful means of quickly processing small packets of data that can come at any time, often many times a second. Whenever a stream is active, the workspace associated with it runs continuously, processing each information packet as a feature. This eliminates the significant overhead inherent in starting and stopping the workspace for each event. And the stream monitors the workspace job to make sure it continues to run, even if it has to restart the job due to workspace error or system reboot. As long as the workspace implementation is efficient, the system can handle very high volumes of activity, such as when many online users are busy making changes in Salesforce and the geodatabase. In our solution, there are two streams, Salesforce to geodatabase and geodatabase to Salesforce. The streams are configured via the FME Server web portal. You can see both streams here, along with the operational status of each. We did, however, run into a few technical challenges during implementation. One such challenge was that neither the Salesforce Streaming API nor the PostgreSQL notification protocol is directly supported by FME, at least not yet. Our solution was to implement a couple of system services in Python to continually forward these messages from their native sources to SQS queues. This is part of the implementation for one of those proxies. Here you can see how we configured the Salesforce to geodatabase stream to run the corresponding streaming workspace. The workspace parameters specify the required web and database connections, as well as the queue to monitor for Salesforce data change events. Each of our streaming workspaces includes an SQS connector transformer to receive queue messages. Note that the mode is set to stream, which means the transformer will run continuously, waiting for events and passing each event on as a feature to be processed by the rest of the workspace. We had to tackle a few more challenges along the way. For instance, our implementation had to avoid synchronizing Salesforce-controlled metadata and read-only computed fields back to Salesforce. So we generated a self-maintaining data dictionary to keep track of which fields were which type. We also had to unpack and repack structured Salesforce fields composed of several values, using combinations of Python callers and other transformers inside reusable custom transformers. Another challenge arose from the fun fact that there are many Salesforce APIs, and we had to use several of those in the overall solution, depending on what we were trying to accomplish at any given time. However, these various APIs are terribly inconsistent in terms of parameter structures and data representation. So we encapsulated and hid these differences within custom transformers as well, and standardized data representation in the local geodatabase. A lot of Salesforce installations are configured to run background processes that further alter data after it's been created or modified by a Salesforce user or API call. For example, one such process might geocode an address after a user has created or changed it, resulting in multiple messages from the Salesforce Streaming API, all caused by the same initial transaction. These exchanges between the two systems can react to each other such that they go back and forth forever, trying to assert dominance over the data. This is known as a race condition in computer science jargon. We implemented an algorithm in the sync workflow to detect and correct for these conditions. Finally, even though FME server streams are self-repairing, we had to deal with situations where the sync streams go down for any length of time due to some uncontrollable situations, leaving the data unsynchronized. So we also implemented a nightly batch migration using FME and the Salesforce Bulk APIs to capture any changes that might have been left behind by such events during the previous day. This was also the best way to get all the relevant Salesforce data into the geodatabase in the first place. Streams are a powerful new feature of FME Server that enable fast processing of high volumes of real-time data. Data synchronization between systems is but one use case for streams, but it's worked beautifully for us. We now have a Salesforce real-time data sync solution that, by our contract with our client, we can reuse for other clients or even within our own business processes. I hope sharing our experiences with streams will inspire you to imagine how you might use this real-time FME Server capability. Thank you for your time and attention.